Dear students, welcome to our class on Micrometeorology of Crops, Solar Radiation 4. In this class, we try to understand in a very comprehensive way the Kirchhoff's law. A lambda is equal to E lambda with reference to our crops, whether it is a cereal crop, pulse crop, oilseed crop, a horticulture plantation or anything. So A lambda is equal to E lambda, Kirchhoff's law. Several times I had explained to you. Now let us see the application point of view on the Kirchhoff's law. In today's class, we try to understand to the extent possible the real application point of view. Now here, usually what we do is the amount of radiation, if you take a crop is like this, okay, the amount of radiation absorbed by this particular crop, amount of radiation absorbed at a given temperature be summarized in terms of emissivity. A lambda, in other words, E lambda, A lambda, E lambda. So what as an agrometeorologist we are interested is how much is absorbed, how much is the dry matter produced. Even in the crop growth models also, the intercepted solar radiation and dry matter, so we take even today in the year 2021 as well. Why I am telling is that the Kirchhoff's law plays an important role in understanding the amount of radiant energy absorbed, and then we can summarize in terms of its emissivity. Now, second important thing is if you just take a white paint, say for example this is the wall, white paint, as far as 0.4 to 0.7 microns is concerned in the visible part or light part, it behaves like a perfectly, it is a very good reflecting. So that means there is emissivity is unity. Now in the far infrared, that's what first I will read. You also please write down. White paint behaves like a white body in the visible portion. White paint, for example, this wall, okay. If you put a white paint, it behaves like a white body in the visible part, like a black body in the far infrared, not near infrared. Far infrared means 3 to 100 microns. 3 to 100 microns we call it as the far infrared. That means same white paint, it behaves in two ways. Okay, what is the Kirchhoff's law? It follows Kirchhoff's law. Now, another important thing is a perfect black body. Okay, a perfect black body is a perfect absorber, perfect radiator. You can say perfect emitter. In other words, perfect emitter and a perfect absorber. In other words, Kirchhoff's law we can apply here as agrometeorology. But crop physiologists, other physical scientists may slightly differ in one or two words that I am using that I have already used. But as far as agricultural meteorology is concerned, the perfect white body would reflect all the incident radiation and have an emissivity of 0. A perfect white body will have an emissivity of 0. However, as I said, white paint which behaves like a white body in the visible portion of the spectrum behaves like a black body in the far infrared region of the solar spectrum. This is what I would like to say. Of course, as black body is concerned, absorbs all of the incident radiation. It has an absorptivity of unity. And as well as it would present from Kirchhoff's law. It is also a good radiator having emissivity unity. A lambda is equal to E lambda, perfect emitter, perfect absorber, perfect radiator, whatever you call it as. We agrometeorologists confine to that particular definition of Kirchhoff's law application for our crops, because we use several instruments, solarimeter, infrared thermometer, for light interception, light meters different in the energy partition. Net radiation is equal to we go for partition, energy stored in the ground, energy utilized in the evapotranspiration, energy stored in the crops, above all and above all, the energy that is utilized in heating the air, okay, net radiation. In that context, A lambda is equal to E lambda. Now, another important thing I would like to discuss with you is, it can be seen that the wavelength at which radiation is emitted by a body, a radiation, see, for example, you take my own body, or you take this plant, you take this paper, you take this wall, okay? A body at terrestrial temperatures, a body at the terrestrial temperatures are very much greater than those emitted by the sun. Again, I repeat it. From the sun, we get long wave radiation. From the terrestrial bodies, we get the long wave radiation. As far as long wave radiation from the terrestrial bodies are concerned, the statement is the wavelengths at which radiation is emitted by a body at terrestrial temperatures are very much greater than those emitted by the sun. From the sun, we get the long wave radiation also. However, from the terrestrial body, we get the long wave radiation, which is greater wavelength. Now, so okay, thus the solar radiation is often called, here I wrote, please you also write, here I wrote, solar radiation is called shortwave, and thermal radiation we call it as long wave. Solar radiation we call it as usually for agricultural meteorological purpose. Suns, presume that sun is there. From the sun, the radiant energy that is coming, usually we call it as a shortwave radiation, even though long wave radiation is there in it. However, the terrestrial radiation, otherwise thermal radiation, we call it as the long wave radiation. Why we call terrestrial body's temperature as a long wave radiation is, after absorbing some energy that is coming from the sun, they go on emitting. That's why Kirchhoff's law. Here also we play, Kirchhoff's law play an important role. Now, solar radiation flux. What is meant by solar radiation flux? The amount of energy that is coming from the sun, watts, okay, is strongly influenced by the atmosphere. Now, see, this is the globe. That is the sun, okay? From the sun, energy is coming, troposphere, stratosphere, mesosphere, ionosphere, exosphere is there. Of course, there is a energy transmission, be it photons, be it waves, whatever may be the theory. Here, important thing is, here, first point is, part of radiation is absorbed. Part of radiation is absorbed. What is radiation? The transmission of energy without the presence of the medium is radiation. So, part of the radiation is absorbed. Where it is absorbed? In the atmosphere. By what? From 30 to 55 kilometers from the surface of the earth, there is a ozone layer. Ozone layer absorbs O3. Okay. Now, in the atmosphere, CO2. In the atmosphere, O2. In the atmosphere, water vapor are there. So, all these things, they absorb radiant energy. Now, this is the first point. Part of the radiation is absorbed and part of the radiant energy is scattered. What is meant by scattering? I have already defined. I don't want to take your valuable time. As part of it is scattered. Of course, direct to diffuse. From there, we get it. In few classes earlier, I have already defined. Now, here an important statement is the amount of radiation that a crop receives. The amount of radiation that a crop receives, okay, he receives varies throughout the day. It varies throughout the day as the path of the radiation changes with changes in the elevation of the sun. The energy that is received by the plant changes with the elevation of the sun. How it changes? Again, here we can go over Kirchhoff's law also. If you take seasonal or annual pattern, seasonal, winter, rainy season, as far as in Asia is concerned, monsoon season, and for winter season, summer season, we call it like autumn, autumn, spring, all these seasons we go for globally. Now, the seasonal and annual pattern results from how the seasonal and annual pattern of solar radiant energy received by the crop changes is because of the orientation of the earth with respect to the sun. This is the earth. Okay, presume that this is the earth. Orientation of the earth with reference to the sun. So, seasonal and annual variations of radiant energy received by the plant is influenced. Now, here another important thing is the corresponding atmospheric path length changes for radiation through the atmosphere. This is an important point I would like to impress upon you. The path length of the solar radiant energy that is falling on the crops on the earth, okay, it depends upon the path length, the radiant energy passing through, path length. So this is what I would like to impress upon you. Then topography plays an important role. What is meant by topography? Several times I told, okay, the relief, okay, the topography, the relief. So how it changes the topography? Say mountain and valley winds. On the one side of the mountain you will find very cool and moist weather. On the other side of the mountain you find exactly opposite, warm and dry. Okay, so like that. Why it is so? Because of the topography has a major influence on the amount of direct radiation that is received on a crop surface. When we sow a crop in an acre or hectare, so in that 1 acre or 1 hectare, the radiant energy, okay, that is falling is influenced by topography of the very small area of 1 acre or half acre or 1 hectare or even say 2 hectares of the crop. This also we should remember while advising the farmers. Now, usually the maximum amount of solar energy is intercepted by surface normal to the beam. Usually for a crop which is radiant energy is maximum utilized or absorbed, a beam which is normal to the beam, okay, radiant energy that is falling normal to the beam. Otherwise, if it is falling slantily, what will happen? When it is falling slantily on the crop, what is meant by slantily? For example, this is the surface, okay, so energy is falling directly, but if it is falling on a slantily, the energy is spread over, not directly falling, not the intensity, the quality changes with reference to topography. This is what, and very interesting points, only last 1 minute of the class, very important points from your JRF, SRF and NET, and even from when you are writing your M.Sc thesis or Ph.D thesis. So please note very important statements. If you have time, kindly write also. Now, number 1, of course, solar radiation, we call it as the shortwave radiation. Terrestrial body radiation, we call it as the long wave, that much. Then, PAR, photosynthetically active region. What is photosynthetically active region? 0.4 to 0.7 microns VIBZYOR. Okay, so the PAR region will have, okay, what 90% of the leaves absorb. The leaves absorb 90% of the light that is falling between 0.4 to 0.7 microns. Please see that much. If you see shortwave IR, okay, infrared shortwave part, that is 0.7 to 3 microns, leaf reflects and transmits. Leaf reflects and transmits. Please write 0.7 to 3 microns, the leaf reflects and leaf transmits, because it is a thermal radiation. It has got thermal effects. So leaf cannot bear it. So naturally it tries to avoid, it tries to mitigate, it cannot adjust to it. That's why 0.7 to 3 microns, which we call it as the near infrared, it is either reflected or transmitted. Which is absorbed? The absorbed is 0.4 to 0.7 microns in the light part, approximately 50%. Now, another statement. Long wave far infrared, otherwise long wave far infrared, where it is from 3 to 100 microns. Again, in that 90% is absorbed by the leaves. 90% is absorbed. So, two crop is there, two bands it absorbs 90%. This is the first one is the 0.4 to 0.7. We call it as the PAR, and long wave far infrared. So these two peaks, but it tries to avoid what it tries to avoid. It tries to avoid 0.7 to 3 microns, which has got a thermal effect, which is heating the plant, which it cannot respond. Last one statement I would like to say. In the just yesterday class I told that convection, radiation and transpiration, these three ways the plant tries to adjust its own photochemical processes of the production of dry matter. That means 0.4 to 0.7 it absorbs, 3 to 100 microns it absorbs, it tries to reflect or transmit to escape from the heat load. Thank you very much for your patience here.